Alex Moylett from Quantum. He will talk about distributed quantum error correction based on hyperbolic Floquet codes.
Thank you to the organisers for arranging this, and I'd like to especially thank them because I was originally due to present a poster here, and the day when I was going to start preparing the poster was the day I got an email asking if I wanted to give a talk instead. So thank you for making my job a lot easier because I already had talk slides I was prepared. So yeah, this is some work that my colleagues at New Quantum and I did earlier this year. You can see the archive link there. We've also gotten this accepted into the proceedings of IEEE Quantum Week. Before I get into that, a little bit about New Quantum. So we started in around about 2019, I think, as a spin-out from the University of Cambridge. We have offices based here in Cambridge and in the United States. And we've grown to a team of about 60 or 70 people. This slide's a little bit out of date now. We've grown a bit since then. But yeah, so primarily what we work on at New Quantum is thinking about distributed quantum correction or distributed quantum computation, and what I'm thinking about in particular is distributed error correction. Finally, just a quick plug as well, we've recently, earlier this year, set up a forum called the Quantum Data Center Alliance, where we've partnered with various groups from across industry and across different hardware types to kind of get open discussions going about quantum data centers and how to design them at scale. This was a photograph taken from our kickoff meeting based in London earlier this year. So I'm going to start this talk with a little bit of a motivation as to why we are thinking about distributed quantum computation. And in order to do this, I want to open up with a philosophical question, one that you might have heard earlier in life. Maybe you've heard this at different points in time. That question is, who would win in a fight? One horse-sized duck versus 100 duck-sized horses. You might have heard this question in a pub or bar at some point, maybe discussing it with friends. The earliest record I can find of this question being asked goes back about 20 years. Now, some of you might have been at a previous conference in this very room, I think, about a year ago, where I asked this exact same question, and I did so with some questionable fashion choices back then. I thought, now, when I first gave this talk, I included this joke, and I thought, well, you know, this was a fun little bit. This is probably going it. Let's move on from it. But then the CEO of New Quantum saw this recording, and she was not happy that this t-shirt did not have any company branding on it. This would have been a lot smoother had I done the unzipping properly. Okay, there we go. Oh. So, yeah, So, why am I talking about ducks and horses today? Well, the answer is because quantum computing has a bit of a scaling problem behind it. So this was a paper taken from some work done by Riverlane on looking at different, the cost of simulating different material systems. And you might notice that this y-axis, first of all, it's a logarithmic scale, and secondly, it's 10 to the 6. So we're looking at kind of many, many qubits here in order to kind of simulate these systems. And this is a trend we're seeing with a lot of the kind of applications that we know of for quantum computing. So some example applications you can think of are problems in material science, like this slide, where we're looking at maybe 10 to the 8 qubits. You can look at problems like drug discovery, where you're working on a scale of 10 to the 6 qubits. Factoring, there was a recent exciting paper from Craig Gidney earlier this year where they reduced the number down to 1 million physical qubits. And then maybe if you look towards solid state systems, you're still looking on the order of tens of thousands of physical qubits. These are not small problems that we are going to be able to fit into a single vacuum chamber or a single dilution refrigerator. These are large problems which you're going to be building large-scale systems in order to solve. So, why do we think that distributed computation is the way to go? Well, the reason why we think this is because we've already seen this play out in the classical world. So, if we think back to how classical high-performance computing evolved, there was a kind of debate at one point between the kind of building large monolithic supercomputers, such as the Cray Mark I, and building distributed high-performance computers, such as the Iliac. And this was a sort of discussion as to whether or not, as to which one of these schools of thought was the right way to go. There isn't, sadly, a source for this quote, but apparently the founder and namesake of Cray computing was quoted as saying, "If you were plowing a field, which would you rather use, 2 strong oxen or 1,024 chickens?" Now, first of all, I'm glad that I'm not the only person who resorts to absurd animal metaphors when talking about this topic. But what I think is interesting about this quote is that if you look at modern-day supercomputers, sure, the power on the individual processors is much better than what it was back in the days of the Cray Mark I. But also, there's significant amounts of kind of computing which comes from running it in a distributed setting. The Frontier supercomputer, the fastest supercomputer in the world, has thousands upon thousands of CPUs and GPUs being able to run lots of small computations in parallel, and that's where the kind of power of these high-performance computing comes from. In many ways, the chicken ended up beating the ox at plowing the field. So, where does this come into quantum computing then? Well, in order to talk about this, I'm going to first of all talk about quantum networks. So, to roughly sketch out the architecture that we are designing for this at New Quantum, we have broken this up into 4 layers in particular. So at the very bottom, you have your quantum processing units. These are the physical qubits that you're building. These might be, say, trapped ion qubits, they might be neutral atoms, whatever your particular hardware of choice is. Then we have the qubit photon interfaces. These are where you generate entanglements between the qubits on your hardware and photons, flying qubits, which you're able to communicate across a network. We then have our modular switching layer. So this is our reprogrammable photonic switching, which is able to route our photons across the network. And then at the top here, we've got Bell state measurements. So being able to measure the photons that come into it, and by measuring them in a Bell state, we are able to infer whether or not we've successfully generated entanglement between two qubit photon interfaces, and then by extension we can pass that entanglement down to entangling qubits between two of our quantum processors. So just to give a little bit of an idea as to what this looks like on the actual hardware side, I'm not a hardware person myself, but to give a bit of a sketch on that. So on the qubit photon interface side of things, we are working on designing really good ions for generating reliable photons, and in particular we are trying to generate able ions in cavities. So I can't remember the exact metaphor, but the stability of these the stability of the cavities that we're generating here are to the level of precision that it would be akin to knowing the height of the Empire State Building to the width of a single hair. So we are making these devices and trying to keep them stable at a very precise level. And then on the networking side of things, we have been busy working away at creating our networking unit. So this is both the switching layer and the L-state measurements aspect. And this is a picture from earlier this year where we announced that we were one of the first quantum technology companies to partner with CERN and integrate their White Rabbit timing technology into our quantum networking unit. So now that we've built the quantum networking unit, the next thing we need to do is run our distributed computation through it. So the way that we can do this is, if you think back to your Nielsen and Schwanning textbooks, you can remember the concepts of qubit teleportation, where if you have a Bell state generated between these two qubits, if you have a qubit in an unknown state on one of your nodes and a shared Bell state between your two nodes, you can teleport this qubit in the top node down to this qubit in the bottom node. The downside to this is that if you get errors across your Bell state generation, then that error is going to map into an error on your teleported qubit. Thus, you've decohered. So the question is, how do we rewrite this setup so that can we do something better than this? Can we do something where we are able to detect these errors and avoid this situation? And the answer is yes. This is through what's known as quantum error correction. So I'm conscious that Joanne will also be speaking about error correction later today, but just to kind of give a brief warm-up to his talk, one of the famous examples of quantum error correction is called the repetition code. So this is where you have a bunch of qubits all in a line, and you just perform 2 qubit parity checks between pairs of them. And if you do this, then if, say, there's an error on one of your qubits here, that will light up two of your parity checks, and you can use that to figure out where the error is on your code. Crucially, however, this only detects one type of error. It only detects, say, a bit flip error. So if you get a phase flip error on one of your qubits, that will go undetected. So if you want to detect multiple types of error, like we might have in a quantum computer, you need to look towards other codes, such as the surface code. And so now, in the surface code, you have this large four-sided patch of qubits and you're performing parity checks between groups of 4 qubits. So this might be a Z-basis check between these 4 qubits, and this might be a X-basis check between these 4 qubits. And this allows you to detect multiple types of errors, but there are a few problems with the surface code, particularly when you try to run it in a distributed setting, which is that in order to actually perform these parity checks, you need these additional qubits inserted, and you need to perform your measurement circuits in such a way that you're able to get the measurement results out of this. And this becomes non-trivial to run in a distributed setting, where now let's suppose that this blue square here, let's suppose this gets distributed across like 3 different processors. How do we best run the circuit, implement the circuit to measure the outcome here? So instead, what we have been looking at in New Quantum recently, has been a family of fairly recent error correcting codes. They were discovered a few years back, known as Floquet codes. So Floquet codes are defined using a free-colorable lattice. So the rules are that each vertex needs to have 3 edges coming off of it, and each face needs to be can be assigned one of 3 colors, such that 2 neighboring faces don't share the same color. And I'm not going to go into the details as to how Floquet codes work exactly, but the key point here is that Floquet codes can be implemented just using weight 2 measurements. So just by measuring, say, these 2 qubits together, performing a parity check between these 2 qubits, and performing a parity check between these 2 qubits, say. And this makes it easier to run in a distributed setting, because now when we distribute this code across our network, we can implement each of these 2 qubit parity checks just using a single Bell state. And so that simplifies the entanglement that we need to generate for this work. The other things we're going to do with these codes are so the hexagonal lattice I showed earlier only encodes a finite number of qubits. We want to develop a code we want to have a code which scales both in terms of the number of qubits and the number of errors we're able to correct as we increase the size of our system. So we have instead looked at what are called hyperbolic Floquet codes. So these are Floquet codes defined on a hyperbolic surface. So in this case, we are using the octagonal lattice here. And this creates a kind of more complex topological quantum error correcting code which introduces more logical qubits and has a better kind of number of logical qubits to the number of physical qubits you have to use. The downside is that the distance, the number of errors you can correct with these codes, isn't as good as you would have for the hexagonal lattice that we showed earlier. This is due to technical reasons. But what we can do is we can then insert parts of a hexagonal lattice into these hyperbolic codes in order to improve the distance, improve the number of errors we can correct. And so this is through a process that Oscar Higgis and Nico Brookman came up with called fine graining, where you're inserting a planar surface into a hyperbolic surface. And so this gives you a trade-off between the performance of your encoding rate and the number of errors you are able to correct. Yeah?
Are we assuming that the parity checks and other error checks don't change the qubits, or do we allow for that?
They do change the qubits, and we do account for that. Yeah, so that's it. So the aim for these codes is to be able to detect when the qubits have changed and how they've changed. So I'm going to just talk a little bit about some of the benchmarking that we've done for these codes. So first of all, just to kind of summarize recap the process from the previous slides. First of all, we start with these hyperbolic Floquet codes. We then introduce fine graining to them in order to improve our code distance. And then we distribute them across multiple processors with some checks implemented locally, and these ones will have a kind of lower error rate, and then some checks implemented non-locally, and these will have kind of higher physical error rates associated with them. So, sorry, that was meant to be an animation there, never mind. So the first thing that we did was we looked at the pseudo threshold for one of these codes. So this is the break-even point, the point where the error correcting code, the logical error rate of your error correcting code does better than a physical qubit. And so we were able to show that there's this trade-off between the amount of local error you can tolerate within each node and the amount of non-local error you can tolerate between the nodes. And the other thing that we show, and crucially what we also showed with this, is that you can tolerate a much higher non-local error rate than a local error rate. So we can account for the non-local errors from our entanglement generation being higher than what happens at a local level. And the second thing that we looked at was the kind of sub-threshold performance. So how well do we expect these codes to do below when they are comfortably below this threshold? So we looked at a few different codes at, I think it was 99% local error rate and 99.7% non-local error rate. And we were able to show this kind of break even. Crucially, we were able to show that there's this point where we are able to hit the kind of scale required for the kind of mega QOP, as I think it's referred to nowadays, of kind of being able to perform 1 million error corrected logical operations. And I can't remember the exact numbers off the top of my head, I'm afraid, but in the paper we give an estimate, we show how many nodes we would need and what the number of nodes per processor are, what the number of how many qubits we need in each node, and how many interconnects we also need between each node. So just to wrap up quickly, we've in this work shown that not only is distributed quantum error correction possible, but it is also feasible to do, and we can do it through an efficient encoding rate. And just to conclude, I believe 100 duck-sized horses will beat one horse-sized duck. And I believe that many networks of quantum processors will beat a single monolith. That's all I've got. Thank you.
Questions?
In your nice diagram you have with teleportation links, are you just using the standard teleportation gadget that you showed in the previous slide?
In this slide.
Yeah.
So what we are using here, so we're not using teleportation here. We are actually, we're generating a bell pair across each of our qubits and then using that bell pair as in a Shor syndrome extraction circuit. So we're using our entangled qubits as the kind of measurement qubit to measure out the parity check.
So, your Floquet hyperbolic code, when you do the decoding, can you do window decoding, or you have to go all the way through?
That's a good question. We haven't looked at decoders yet. We have been the decoder we used for this work in particular was pi matching, and we just ran that offline after the simulations had completed. There isn't anything that would stop us from being able to use window decoding, I think, but it's not something we've looked at.
Maybe I have a question. So
yeah?
The bottleneck seems to be to convert your qubits to photons. Now, what is the efficiency that you have for that for a moment? Just to kind of put this into context with the other kind of part of your talk.
I don't know the hardware numbers off the top of my head, I'm afraid.
No, but isn't that the crucial part of the whole
approach? So the slowest part is the kind of heralding entanglement. We are kind of anticipating that. One of the things that we are trying to kind of understand is what's the trade-off between kind of slow entanglement and generation. What happens if we kind of account for slow entanglement generation, particularly like entanglement generation is a probabilistic process. So what's the trade-off there between kind of how many entanglement failures can we tolerate as part? But
what is the record? Because there has been hundreds of papers of people trying to turn, let's say, qubits and an ion trap to something like that. What is the optimal efficiency of doing this? What is the best possible efficiency that has ever been reported for that?
I don't know, I'm afraid.
But what is it? What you need to be able to put this in this framework of these codes? How much efficiency would you need?
So I don't know about the efficiency. What I know is that for the threshold we had we had about 99% error fidelity. I don't know what that translates to in efficiency.
And maybe another question, what is very strange is that you can deal with more errors for the non-local errors than the local errors. Can you give an intuition about this?
You can, it's because non-local errors are concentrated in your code. So there's only going to be so you've got a kind of small parts of your code which have higher error rates, and then the rest of your code has lower error rates. So as long as and crucially also where those higher error rate parts of your code are. And so because of that, you can kind of account for that in your decoding.
Yeah, the question is, how many non-local checks do you have versus local checks?
That is a good question, and I can't remember off the top of my head, I'm afraid.
Yeah, sorry, just follow the same strand of questions. Thanks, Alex, by the way. When you say peanut local, does that mean the connections that cross between the processes?
Yes.
Okay.
Yeah.
Okay, so if there's no more questions, let's have a break. Let's thank the speakers first, and then have